Hello everybody, my name is Quinn, and today I'll be going over a little bit about cylinder head inspection as well as some valve train maintenance. So to start off with, I'll give you a quick rundown on what the cylinder head is and what its purpose is. So the cylinder head is what houses pretty much, it houses your valves, your rockers, in some cases your cams, and what this does is sits on top of the engine block and will seal off your combustion chamber. So this is your main source of airflow in and out of the engine. All right, so I'll go over some quick key differences between these two heads specifically, as these two styles of head are fairly common. So to start off with, we have a 2-valve head and a 4-valve head. So that is one of the big differences between heads, is usually how many valves there are. Then you also have the material it's made out of. Right here is a cast iron head, and right here is an aluminum head. Some of the pros for cast iron are that it's fairly cheap to make, and they are fairly durable. They're not as malleable as, say, an aluminum head. Some of the downsides of them are they're very heavy and they don't dissipate heat very well. And so moving over to the aluminum head, what you have is pretty much the polar opposite of this. You have a lightweight metal, and you have a metal that dissipates heat very well. And this heat dissipation advantage over iron heads is enough to, in some cases, you can get away with a higher dynamic compression on the same octane fuel as off of an iron head with an aluminum head. This is because the head helps cool off the combustion chamber a lot better than in a cast iron head. Some of the downsides for aluminum are that it's fairly expensive. It's more expensive than making a cast iron head, making it, it's fairly common on modern vehicles, on most engines, but for the most part, it's reserved for somewhat high performance engines, force induction, stuff like that. And another thing with aluminum is that it's not as strong as cast iron. Aluminum under overheating conditions tends to warp a lot more than a cast iron head. With a cast iron head, you might be able to get away with a little bit of overheating before it starts to cause considerable warpage, while an aluminum head, after overheating, will tend to warp a lot more. So I will also go over later in the video some of the inspection methods for both these heads. For crack detection, we have Magnafluxing for iron heads and dye for the aluminum heads. And for warpage, we have what is called a straight edge, which is a piece of thick steel that is known to be straight, and I will go over how to use that later. That goes in conjunction with the feeler gauge. And I will also show you how to adjust valve lash on a VTEC engine. Although valve lash isn't very common on most modern engines because of hydraulic valve trains, on VTEC engines you do still commonly have to adjust the valve lash for those rockers. And I will also go over how to replace valve seats in cylinder heads. As with both these heads, replacing the valve seats is fairly similar, as both of them do have cast iron valve seats. With the aluminum head from factory, it has cast iron seats that are pressed in. As like I said, aluminum is a fairly soft and malleable metal with a lot of load going on it. With valves smacking into aluminum, it would most likely tend to bend or dent. So they use cast iron for the valve seats. Here we have our first crack detection method on our cast iron head here. This method is called Magnafluxing. So what you have here is a electromagnet, and you also have some iron powder, steel powder, anything magnetic really. is a powder here. This one's specific for Magnafluxing. And so what you want to do is, after you've visually inspected your head for any obvious damage, such as dents, dings, any serious problems, you might want to look for cracks. And so, as you can see right down there, there's a very tiny crack. And if it's hard to see, that's okay, because this method will help us sort of visualize it a lot better. So, your first step with doing this is to have your head in a decent position. And now that we know, say you wanted to check for cracks somewhere else where like you couldn't see a crack, you would take our electromagnet and you would turn it on, and be very careful not to put your hands under this or anything like that, because these can be very dangerous. They're very strong magnets when they're energized. So now that we have our magnet going across our combustion chamber here, we're going to take our little puffer here with it's filled with the magnetic powder, and you're going to want to spritz it near our crack. This method can also help visualize if a crack is bigger than you think, or is bigger than it looks. It'll help you visualize how truly big the crack is. So now we can truly see that crack. It's going all the way down from the actual head right here down through the valve seat. So on a normal head, if you can't see the crack, what you'll do is you'll do the same thing across main problem areas. For two valve heads, it's usually either between the two valves, that's a fairly common area for them to crack, or down the valve seats. The valve seats do commonly crack as well after a lot of wear and tear. So that is Magnafluxing. Now I will go to showing you the die method for aluminum heads. Alright, so now we're here at the aluminum head, with the aluminum head and our die system here. For this die system, it's a 3-part system. You start off with a cleaner solvent, which is specifically made to, condition surface, and in this case, it would be made to get off any other of the dye off of the head here. So I'll just give it a spray down and a wipe. You do want to tend to try and get as much dye as you can off of here, because the more dye you have excess from maybe a last time you tried it, the more chance there is that you might find something that could be a false reading or something like that, or the dye might not stick and go into the crack here. And then for this, next up you have your penetrant dye. For this, it does say to wait about 5 minutes, 1 to 5 minutes for normal cracks, and 20 minutes for very small cracks. I really can't tell you, what is a normal crack and what is a small crack. I assume for, this is something like a normal crack where it's not crazy small that you can't see it, but it's just big enough that you can. So what I'm going to do is spray this on and wait about 5 minutes for it to fully set, and then I'll come back. Alright, so it's been about 5 minutes. So after your 5 minutes is up with your dye, you're going to want to wipe as much as you can off of here. Give it clean. And if you do still have, big excess patches of dye where you don't want it to be, you can take a light spritzing of the cleaner and very lightly go over and clean it. Unfortunately, for right now at least, we don't have the developer. So since this is a three-part system, you have the die right here. You have the die, and then after the die comes the developer. With the developer, this essentially makes sure to activate the die itself. And so when you see a crack, you'll be able to see red sort of bleeding out of the crack to identify it, and it will be a nice bright red. It's a very similar method to Magnafluxing, where the whole goal of it is to detect small hairline cracks that could cause issues later down the line, and to sort of highlight them. It's a fairly similar method. It's just since aluminum is non-magnetic, you can't use Magnafluxing with an electromagnet. You have to use something like a die. Hey, it's me in post. I wanted to explain a little bit more about an alternative method for aluminum head crack detection. For aluminum heads, you either have a penetrant dye like I showed, or you can do a UV dye which activates to UV light. It's fairly similar to AC system UV dye or oil dye, where all you really do is put it in, you spray it. On this case, it'd be like an aerosol. You spray it down, and when you get it into the crack, you use the UV light to activate it and show it better in the head. So what we have now is our straight edge. So with this is a straight piece of steel. You can measure the straightness of a engine block as well as a cylinder head with these. So basically what you do, it's actually pretty simple, is you want to take your straight edge and put it across diagonally. You can do it diagonally one way, you can diagonally two ways. The more measurements, the better. You can measure ends, so you can measure vertical going like that. You do that. For the most part, the manufacturers just recommend doing something like this, where you go across corner to corner with the straight edge, and then with it on the cylinder head, you will take a feeler gauge to the manufacturer spec. Make sure to look at manufacturer spec for warpage tolerance, because not every cylinder head and not every manufacturer is going to have the same tolerance. One manufacturer might be different, one engine might be different from another. So just keep that in mind when you're researching and trying to see if your cylinder head is out of spec or not and needs to be flattened out at a machine shop. So I'll use this as an example. I'll take the 3/1000 of an inch feeler gauge, and what you want to do is take your feeler gauge and see if it slides under anywhere under the straight edge. See, it slides down under here, but like I said previously, I'm not sure what vehicle this cylinder head came off of, so that could be still within spec. I'm not entirely sure, since like I just said, don't know what vehicle this is from. But if this was your vehicle, for example, and the manufacturer said 0.003 of an inch is the tolerance, if your feeler gauge is able to pretty easily slide under the straight edge, then your cylinder head is more than likely out of tolerance. So this one, it does slide under, but tends to have a lot of resistance. Right here, it's pretty loose. That could also be by how I'm holding it, since the cylinder head can't sit flat. That's another thing too, is if you're going to do this, try and make sure that you can sit your cylinder head flat. I know I'm not doing that here, but it's because this cylinder head doesn't seem to want to sit flat. But if you're doing this on your own, that's what you want to make sure of. It just makes it much easier to hold the straight edge rather than having to fight it falling down. So you slide it under here, you do that, slide it under here, and that goes for every other direction of measuring it. So if you do it this way, you want to measure every point of contact with the actual cylinder head. And then even if you do that vertical, you can do a vertical down here, wherever. Same thing. You want to make sure that wherever you're measuring, you don't have any huge gaps that your feeler gauge can slide under really easily. If there's quite a decent amount of resistance, it's more than likely that you're teetering on that edge of within spec and out of spec. So keep that in mind for if you get a straight edge and are trying to find warpage on your cylinder head. Alright, so I real quick wanted to mention some on the valve seats for both these heads. So with a iron head, you will have to take it and get it machined out. With the valve seat, you have to get it machined out to a flat surface like there, and then from there you'd press in a new one to fit that bore that was cut out. Now on an aluminum head, you can do the same thing, or what a lot of people do is put it in an oven, heat it up, and then the valve seats will just usually drop out, or you can tap them out. And then the similar thing happens with these valve seats is you would press these in to the aluminum head. Alright, so here we are now at a overhead cam Honda engine where I can adjust the valve lash and show it in a very easy way. The reason I'm showing this specifically is because most modern engines, aside from VTEC engines, do not use valve lash adjustment. Their entire valve train is hydraulic, so it all, with the proper oil pressure, will adjust itself. So on these engines, here you have your rocker arm, which sits down here on the cam lobe, and that is what obviously opens and closes your valves. So when you are adjusting lash, you want to make sure that you are on the base circle of the cam lobe. You don't want to be up here. You don't want to be, here. You want to be about, halfway, and, both ways. This ensures that you're not adjusting your lash too loose or too tight. The way you can do this is you can put the piston on the at top dead center for the cylinder you're working with on the power stroke. Make sure it's the power stroke, because a lot of engines will have, on the exhaust stroke, will have some valve overlap. So you want to be careful with that. Especially, not so much with overhead cam engines where you can specifically see where the lobe is. But this is more for overhead valve engines where the cam is in the block and it's a bit harder to see where the lobe is. So for overhead cam, it's a bit more crucial that you do know where your piston is at top dead center. So from here, to adjust the lash, you actually take this lock nut and you will loosen the lock nut, and this threaded rod with the flathead cut out into it will adjust the lash. So you will turn in the screw to get less lash and turn out the screw to get more lash. And so when you're doing this, the manufacturer has a specification for what lash should be set at, and this lash ensures that your rocker arm gets more life, your valves get more life. It ensures that your valves also are not open when they shouldn't be, or they open at the amount that they should be opening at. It also saves your cam lobe, as having too much pressure on the cam lobe can wipe it and turn it into just a complete circle. So once you have your manufacturer spec, you'll take a feeler gauge that is obviously to the thickness of the manufacturer spec, and you will slide it between the rocker arm and the valve spring. If you feel a little resistance, that's usually at the right lash adjustment or really close to it. So you want to feel a little resistance. Feeler gauges can take a little bit to get used to, but for the most part, that's how you do it. You feel a little resistance, not too much, not too little. I should be able to slide it with a little resistance to it. So when you have your lash adjustment set to where you want it to be set, you will take the lock nut and you will take the wrench you have. A lot of times, I can't really show it because I'm holding my phone, but a lot of times When tightening this lock nut, you'll want to hold the actual threaded screw in place with the screwdriver, just to make sure that your lash adjustment stays the same and doesn't change any. And when you do properly adjust your lash, you will get play in the rock arm, but if you go ahead and open the valve, the rocker arm will not have any play. It's hard to show because this mock-up here that I'm working on to show this is a bit stiff, but when you adjust your proper lash, what'll happen is the rocker arm will move, and then once it starts to hit the tip of the cam, it'll put pressure on the valve spring in the rocker, and your rocker won't move anymore. It'll just remain silent. So once again, this ensures cam life is proper, valve life, proper operation of the engine, as well as rocker life.